Welcome to this video. So this video, what we're going to do is start talking about some of the mathematics of actually calculating entropy values. So entropy is, right, kind of one of those weird things that probably you don't feel like you have a good grasp on. We've looked up numbers in tables. In this video, we're going to see how we calculate it for at least a couple idealized systems. So we'll start by thinking about some properties of entropy. So entropy, we say here, like enthalpy, like temperature, pressure, these kind of things. What kind of function is it? It is a state or point function. So what does that exactly mean? Well, let's look at this hypothetical path over here on the graph at the right. This is a pressure temperature graph. It could be whatever variables we happen to choose. Just trying to indicate we have a state 1 right here, and we have a state 2 right there. So if we think of some path, right, between these states, things happen. Say, we go on some meandering path. I don't know, we do some loops, and we end up there at state 2. Depending on which path we take this loopy path. We could do a different path. We could take, a path where we're constant pressure, and then a path where we're constant temperature. So we could take something like this and get to, I don't know, somewhere over here. We'll call that maybe 1 prime. So 2 different paths that we could get between state 1 and state 2. The cool thing about a thing like entropy, because it's a state or a point function, it has a definite value at point 1 and a definite value at point 2. So the change in entropy between 1 and 2, like S1 and S2, those are going to have exact definite values regardless of which path we're taking. So the cool thing about this is we can calculate along the easiest path. So it makes our lives easier. We don't have to calculate entropy along any path. We can simply calculate it along whichever one happens to be the easiest for us to calculate it along. Right? We can kind of make our math lives easier, which is always a good thing. So let's think about, okay, what would be the easiest path? The easiest path is going to be a reversible path. So let's think about some equations that we know along a reversible path. We've mostly dealt with kind of this matrix of equations. We've dealt with this equation quite often. The integral form of work equals the integral from state 1 to state 2 of P d specific volume. Again, let's just kind of be a little bit extra explicit here. We're talking about the reversible work from state 1 to state 2. This is the integral form, the one that we've most commonly used, but we could take the differential of each side, and we would get, I'm going to write some funny notation, just write it with me. We'll explain what it is, kind of this funky looking dw reversible equals P normal d specific volume. Okay, I'll point out exactly what that symbol is. Just write it like that. What we haven't done as much of is the integral form of Q, but we have done it. If I write it, you'll probably remember from a while ago. We could look at, say, Q from 1 to 2. Along a reversible path would be the integral, again, from that same state 1 to 2 of T ds. Right? Remember, we used this equation when we were looking at Carnot cycles, and we could say that Q equals T delta S. So we have used this before. Same equation applies whether we're talking about a CV, control volume, or a control mass. We could similarly write the differential form. It would be the same funny looking dq, and we'll specify that this is reversible, would be T ds. Okay, I said I would make a note what that funny looking D is. This funny looking D means a path differential, or an inexact differential. It's a mathematical way of saying that it's a path-dependent variable. Q and W, right, the two crazy paths I drew up there, both of them are going to change depending on which path we take. We're taking a specific path. That's why we denoted it dq reversible. We can do an energy balance. We do energy balances all the time, so let's just do one. An energy balance along a reversible path. So delta U equals Q between those 2 points minus W along our path. Or we can rewrite this as Q equals delta U plus W. Right? We can flip-flop it around with some algebra, or we could divide by mass and have something like, well, let's put Q out front. Q12 equals delta little u plus little w, or we could take the differential. dq reversible equals du plus dw. Well, these, I guess, let me erase that. Shouldn't have had that, because that's true along any path. It doesn't have to be a reversible path. We can rewrite our energy balance along a reversible path. So we could rewrite this as dq, basically substituting in these two equations, where instead of dq, we would have T ds equals du. I promise this will make sense in a little bit, hopefully at least, plus P dV. Okay, so we just did some stuff. We did an energy balance. We said we have equations for reversible work and heat transfer, and we kind of smushed those together in a differential form. Again, it'll make sense in a little bit. We could do the same kind of thing or a similar type of thing with enthalpy. So we have a definition here for enthalpy. H is defined, that's the three little equal sign. H is defined as U plus PV. So dH is du plus d quantity PV, which by the product rule, dH equals du plus PdV plus V dP. Okay, that's just the product rule. So we have just, we're going to kind of smush it together with the equation we just had, the TDS equals du plus PdV. So let's have du plus PdV on one side. So dH minus V dP equals du plus P dV. I don't know about you, but I think it's kind of fun to say. V du and PdV and VdP. All right, so let's smash these together. If we combine them with the above equation, we would have TdS equals, instead of du plus PdV, we have dH minus the dP. So we just did some fun algebra and a little bit of calculus. The question is why? And if you think about what we had back up at the top when we were doing those energy balances, we have Q and W, which are both path dependent. And now we have two differential equations which do not depend on path. We now have equations which are not path dependent, which is kind of cool. So we take this energy balance where both heat and work are path dependent. We can smush it together, and now we have equations that have entropy, which is not a path dependent thing, it's a state function, internal energy, state function, pressure, state function, temperature, state function, volume, state function. Everything's a state function or a point function. Nothing depends on path anymore. So these are two special equations. They're called the Gibbs equations. They look a little funny, but really what they are is just energy balances along a reversible path. We can use them, though, to do some cool things. So we're going to use these, again, they're just energy balances along a specific path. They just look a little weird. We're going to use them to find delta S. So let's start with this equation. TdS equals du plus PdV. We can rearrange that so that ds equals du plus p dv over temperature. We can now integrate that. So delta S equals the integral of du over t plus the integral of p dv over t. And this is right. This is how we calculate entropy. That equation right there. So that equation allows us to calculate changes in entropy. One of the kind of interesting things to note is we can't actually calculate entropy exactly, like a value of entropy. We can only calculate changes in entropy. We can only calculate delta S. We can't directly calculate S. But we can calculate the delta. This is the equation that we use to do that. We're going to explore two idealized systems. So we can that we'll use in this class to calculate it for these specific idealized systems. This equation that I have boxed right here and starred, that's the general equation. That's the general equation. That's the always true equation. These next couple are going to be true in specific cases. The first specific case is an incompressible solid or liquid, right? Which would be, if it's incompressible, the change in volume dV is 0. So then that whole second term, the PdV over T, drops out because dV is 0. So delta S becomes the integral of du over T plus 0. We know that du is Cv dt. It's the definition of internal energy, heat capacity times the change in temperature. So we can actually go and do this and find that delta S is the integral from T1 to T2 of CV dt over T. If we have, again, now this was a special case, incompressible. If we have another special case layered on top of that, this is where we get into really a lot of special cases. If we have this other special case layered on top of it, where the heat capacity CV is constant, then we can pull it out of the integral and solve it, and we would get that the delta S is CV, and we have 1 over T, so that's just a natural log. CV ln T2 divided by T1. So this is the more general equation in the box, the more specialized equation not in the box. That's one idealized system, an incompressible solid or liquid. The second one would be an ideal gas, right? An idealized version of a solid and liquid, now an idealized version of a gas. For a gas, pressure and volume does change, so we have to use the ideal gas law to be able to handle that. So du over T plus the integral of P dV over T. Make it a little bit more explicit that I'm doing a V. We know from the ideal gas law that PV equals RT. So we can do some algebra. P over T equals R over V. So we can substitute R over V for P over T because ideal gas law. And we can rewrite this equation. Delta S, instead of du, we'll have CV dt over T from T1 to T2. And now instead of P over T, we'll have the integral from V1 to V2 of R over V dV. This is an integral that we can solve. R is a constant. So if we want to solve this kind of more generally, the heat capacity is not in general a constant. So we would have to leave this part as an integral, dt over T. But the second part, R is a constant. So for an ideal gas, we can just solve that. That's R. Again, 1 over V, that becomes a natural log. V2 over V1. So if we want to calculate changes in entropy for an ideal gas, there's our equation right there. We can, again, this is a special case. We can do a special case of a special case. Lots of equations here, especially for entropy. But if we have a constant heat capacity, which we often do, then we can solve that first integral as well. And we would solve it, we would get another natural log. T2 over T1 plus R times the natural log V2 over V1. So again, the one in the box is a special case. The one below it, which I'll underline here, those are both the constant heat capacity, both important equations, ones that we'll use quite a bit. We did both of these equations, well, really the second one, we used the one of our two Gibbs equations. We have another one, so we could have used the other one just as well. And if we go through and do that, right, it would have been dH, that's a temperature, capital T. We could have used our other Gibbs equation like this. We would have gone through the same thing. This is now the integral of dH over T minus the integral of V dP over T. So we would have to plug in what each of those are. So we're going to substitute in for dH. Now not CV, that will be CP. We're going to use the ideal gas law. So V over T is equal to R over P. So this will be minus R times the natural log of P2 over P1. So this is an equivalent equation to the one that we have boxed up above, again for an ideal gas. And we could go through, if we have a constant heat capacity, we could solve this. This would be Cp times the natural log of T2 over T1 minus R times the natural log of P2 over P1. All of these equations for entropy, they're all in some ways derived from energy balance equations, which I think is kind of neat. Right? We see energy balances really popping up all over. The thing to remember, and the thing that's going to be hard to keep track of with all of these, is when each one applies. So we have, right, up here, our general equation, which is true. And then we have down here the second one for incompressible solids or liquids. And then we have really like 4 equations there, and there for different types of ideal gases. Ideal gases or ideal gases with constant heat capacities. So lots of equations, kind of tricky to keep track of which one is which, but hopefully this helps you keep them straight. And we're going to be able to use these to be able to calculate changes in entropy for different systems.